Here am I teaching something to engineers that they don't care about. Because why would they care about fundamental electrodynamics, blah, blah, blah? It's some intellectual pursuit. They care about something totally different. Which it turns out that today all of us care, physicists, applied mathematicians, computer scientists, the crooks, the cryptologists, secret agencies of this and that, which is, we live in a world of big data, and it's now accessible. We have to do deep learning, we have to do all kinds of things. And whenever that happens, we as humans, we can write formulas, but we need some kind of visualization, many of us, to really understand what this means. And it's extremely hard to navigate dimensions larger than 3. In 3 dimensions, we still have, our depth perception, so our brain can reconstruct 3-dimensional objects. So cat and cloud look different. But even 4 dimensions, which is what you need to understand special relativity, tends to be, mind-boggling for us. And now we are supposed to look at billion dimensions, or on the 3rd and 5th floor of how people routinely look at hundreds of thousands of dimensions because they discretize fluid equations by putting fluids into little boxes and integrating partial differential equation this way. And that means of order 100,000 degrees of freedom just to get a decent integration. So, how do you look at that stuff? Everybody looks at it stupid, wrong way, and it's impossible to deprogram graduate students. So, for example, I'm trying to deprogram Grigoriev and Schatz graduate students, but there is a wall, which is the 2 professors, so I can't reach to teach them how to look at this data. But eventually they'll figure out themselves. So, what is the problem? Do you think, complex analysis of gamma function nothing to do with it? So the problem is, you're doing a simulation, computer is integrating 10,000, particular example that we actually did, 10,247 independent degrees of freedom interacting by some nonlinear ordinary differential equation. That's an approximation to a partial differential. 10,000 are needed to resolve 3-dimensional structure of a turbulent fluid. Now, in 10,000 dimensions, you can, put, it's a vector space. So you can just look at 2 vectors. And, I pick a vector, and Shonding picks another vector. For some reason, we have psychological reasons. We think this direction is important. He thinks this direction is important. So how big is his vector going to look to me is the question. In other words, if I look at 2 vectors and I normalize them, they're in 2 and 3 dimensions, you have no problem understanding what it is. Every 2 vectors have an angle between them, which is a cosine between them. And if you make them unit vectors in length, then you're measuring this cosine. And now there's a probabilistic question, which is, how likely are we to pick our directions? Now, it's just a vector space. It has lots of dimensions. So the simplest assumption to take is I'm equally likely to take any direction in that space. So that's the assumption. And now the question is, what's the angle between your vector and my vector? if they are 90 degrees to each other, that means I don't see a vector at all. It's a zero projection onto my axis. If we have chosen, comparable vectors, so they're parallel or almost parallel, it'll be of order 1. Your vector, I'm 6 feet, but you will look like you're 5 feet tall because you're some distance away from me, and that's all. So to do this, you have to do, some elementary geometry, but it's in higher dimensions. So it's a unit vector. It's within a hypersphere. The only trick is it has to be in not 2, not 3, but in any dimensions. You have to compute the total angle of a sphere, of a planet, in 10,000 dimensions rather than 3. And that's, this number is getting large, and that's going to be the parameter in our Laplace transform. And what is the angle? Well, you can compute it by taking all the d dimensions, and then you can put a Gaussian this d dimensions, so that's a Gaussian. And then you can use, how to compute Gaussians, so you can evaluate this in 2 ways. You can evaluate it as it stands in Cartesian coordinates, so they're all independent Gaussians, or you can go to polar coordinates and evaluate the angle around them. So in Cartesian coordinates, this is obvious. Each direction is the same. You always get square root of 2 pi, but there are d of them. So this integral has value 2 pi dt. In polar coordinates, you take a radius and you take the angle. And because you're now doing an integral that has a radius to it, it turns out you're computing your Laplace transform that you didn't ask for, but you're computing gamma function. Or, that's your problem set to verify this. So in that case, you can compute the total surface of a hypersphere in terms of a gamma function. And you can either compute the surface or you can compute the volume, the same, but you get a formula for solid angle. It says that solid angle has to do with combinatorials, and odd and even dimensions are different, doesn't matter. But the main thing you have to see here is that you have a combinatorial, and now you have to compute a limit of this thing for large dimensions. So that's your parameter. And you use a Stirling formula because you have combinatorials. So how do I estimate 2 angles picked at random? I'm the professor, so my angle is going to be oriented along the axis 1. This is my axis. I can always choose one of them. Then the graduate students, angle. So it has to be angle between me and graduate student axis, but it can be any place with equal probability in the angular coordinates. So there is a little strip which is around the meridian on this hypersphere, and that vector can be picked any place on that strip. So probability to find 2 vectors at a given angle is proportional to the area of this meridional strip of width delta theta. So, you have the formula, so there's no problem to compute it. It turns out to be a ratio of 2 gamma functions, so that's totally exact. Do the Stirling, and what do you find? This ratio is maximized at angle pi over 2. So, the most likely outcome, the peak of the Gaussian, is at pi over 2, and the variance of this hill, the width of it is 1 over d. So I pick my vector, my graduate student picks her vector, and that vector is this probability 1 orthogonal to mine, meaning it looks like nothing. I'm looking at the direction. In first approximation, it's always orthogonal. And when I look at its fluctuation, its height is of order plus or minus 1 over the number of dimensions. So I'm in 1,000 dimensions. And whenever I look at any graduate student randomly distributed any place, their height is not 5 feet or 6 feet. Their height is 5 feet divided by 1,000 or 100,000 because my calculation is there. So in other words, if you're not thinking, and nobody is thinking until they're forced to think, and you're a humble plumber, and you're simulating turbulence, and you're trying to put a picture that you want to publish in Phys Rev Letters or Nature, pseudoscience or whatever is best for your future career in this predatory publishing, then with probability 1, all your results are of order 0. However, if you follow this course, you realize when you have a large data set, you should do SVD on that data set, singular value decomposition. What does SVD do? Your data might be concentrated on some smaller dimensional subspace in this big 100,000 dimensions. And that's what almost always happens in image recognition, in computer science, and in neuroscience, and in turbulence. The data is bunched someplace because there are some kind of shapes that all look pretty similar. And there are some pictures you never see. So you use singular value decomposition, and in this vector space, you choose a dominant direction, and you send the grad student over in that direction. The second grad student, she's checking the fluctuations. That's the second singular value. And you put an ellipse, so that's the simplest thing. Now, what machine learning today does, it says, I should look at clusters of data, their orientation, do graphs, etc. So there's much more elaboration to it. But just taking anything to represent your high-dimensional state space doesn't work. And you prove it using settle points, so you prove it using complex analysis, no matter who you are. But it's called volumes of spheres if you reject the idea that gamma function exists and you only want to have integer spheres. I'm done, and I'm now open to all criticisms and attacks on the people who don't believe in science.